Here's something that shouldn't be possible. This fern, every frond, every little leaflet, comes from just 4 rules. 4. No leaf drawing, no botany. Just 4 tiny instructions, and a game of chance. Remember how we drew the Julia and Mandelbrot sets? For every single pixel, we ran a sequence and checked if it stayed bounded. Millions of points, tested one by one. It works, but it's slow. So here's the question. Could we draw a fractal that just paints itself? The trouble with the Julia set is that it pushes points away. Take a point that's not on it, run the map, and it flies off to infinity. The set is a repeller, a knife edge, not a magnet. But flip the map around, run it backwards, and everything reverses. Now the same set pulls points in. Backwards, the Julia set is an attractor, a magnet. Wherever you start, you get sucked onto it. There's a catch. Squaring is 2 to 1, so running it backwards is 2 valued. Every point has 2 pre-images, 2 branches, like the 2 square roots of a number. Chase both, every step, and after n steps, you've got 2 to the n points. That blows up fast. So here's the clever fix. Don't chase both branches. Each step, flip a coin, and follow just one, chosen at random. It sounds reckless, but because each branch pulls inward, the point stays glued to the set, and random coin flips over thousands of steps wander into every corner of it. They call this the chaos game. Now generalize. Take a handful of maps, call them F1, F2, and so on, and make each one a contraction, meaning it shrinks distances. Give each a probability, and make the probabilities add up to 1. That's an iterated function system, an IFS. The recipe is dead simple. Start anywhere. Then, over and over, roll the dice to pick one map, apply it, plot the point. Throw away the first few. They're just a point homing in. Everything after lands on the attractor. That's your fractal. Why must every map shrink? Because shrinking forgives mistakes. Any error from a bad starting point gets smaller every step until the point is swallowed onto the attractor. And why does randomness fill the whole thing? Because the attractor is made of shrunken copies of itself, and a random enough sequence eventually visits every copy, and every copy of every copy. And here's the beautiful part. How do you find the maps? The collage theorem from Michael Barnsley says, if you can cover a picture with shrunken copies of itself, then the attractor of those maps looks like your picture. The better the collage, the better the match. Drawing a fractal becomes finding a few affine maps. Which brings us back to the fern. 4 affine maps do the whole job. 1 draws the stem, 1 shrinks the entire fernaloo, and 2 build the leaflets, left and right. Watch it fill in, point by point, a whole living shape out of 4 little rules. And the same game gives the Sierpinski triangle. 3 maps, each having the picture toward one corner, each with probability 1/3. Same dice, same rules. A totally different fractal falls out. So that's the quiet magic of iterated function systems. You don't draw the fractal. You write down a few shrinking rules, roll the dice, and let chance do the drawing. Order, falling out of randomness. Sometimes the shortest way to describe something complicated is a handful of simple rules.